I am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on broadside arrays and Endfire arrays. So we know an antenna array is a system of similar antennas oriented similarly to get greater directivity in a desired direction. And it also may be defined as it is a radiating system consisting of several spaced and properly phased radiators. The total field produced by an antenna array system is the vector sum of the fields produced by the individual antennas of the array system. So, an antenna array is said to be linear if the individual antennas of the array are equally spaced along a straight line, and the individual antennas of an array system is also termed as the elements. Thus, linear array is a system of equally spaced elements. So, there are various forms of antenna arrays. The major classifications are broadside array and Endfire array. So, in a broadside array, all the antenna elements are kept at equal distance. So, it is a linear array, and the current amplitudes given to the each element is same phase and having the same amplitude. And for this type of array, the maximum radiation is in the perpendicular directions of the antenna array axis, and this antenna provides minimum radiation towards the antenna array axis. So, in converse to this broadside array, there is another array called Endfire array, but the similarity is this is also linear array, because in Endfire array also all the elements are equally spaced. So, it is a linear array. But the difference between broadside array and Endfire array is, in Endfire array, all the elements are having the same amplitude as like broadside array, but while we considering a phase, there will be 180-degree phase shift difference between the adjacent element in an antenna array system, and the maximum radiation for Endfire array is towards the array axis, and the minimum radiation is in perpendicular directions to the array axis. So, these two antennas are antenna array are the major classification of antenna arrays. In addition to this, we have third type of antenna called collinear array antenna. So, in collinear antenna arrays, the antennas are arranged coaxially, that is, the antenna array is mounted on one to end in a straight line, and the individual antennas are fed with current of equal amplitude and equal phase as broadside array. So, this antenna array is similar to broadside array, but the only difference is the antenna's arrangement. So, the arrays are antenna elements in an array are placed and are stacked one over the other, and we have the analytical purpose, and for analysis we take two element array of isotropic point sources, and the diagram represents there are 2 point sources equally separated from the origin. So, and the total distance between the arrays are taken by d. So, the distance between the individual antennas, that is from the origin to individual antenna, is d by 2. And if we consider the diagram, the field due to the antenna 2 is faster than antenna 1 because of the phase difference between the antenna 1 and 2. So, now our need is to calculate the phase difference in order to get analysis of this antenna. So, to calculate the field at greater point P at a distance r from the origin, and here the origin is taken as the reference point for phase calculation, and the path difference is equal to d by 2 cos theta and plus d by 2 cos theta meters, and both are added, it is equal to d cos theta meters. So, now the path difference is in terms of meter. To convert the path difference in terms of lambda, we are dividing by the value of lambda. So, this becomes d by lambda cos theta wavelengths, and the phase angle is multiplying this path difference by 2 pi. So, we get 2 pi into path difference, that is 2 pi d by lambda. We know d by lambda, 2 pi by lambda is beta, so it is beta d cos theta. And now we are calculating the total field. Total field E is the field due to the individual antennas. So for the first antenna and the second antenna, both are having the same amplitude of voltage. So we have E1 and E2 same equal to E. And for the first antenna, there will be phase lagging and when compared to the second antenna. So e power minus j psi by 2 for the first antenna and second antenna, the phase is e power plus j psi by 2. Here psi is the total phase difference. And while calculating, we get the total field is 2 E naught cos of beta d cos theta by 2. And this E1 and E2 is E naught. And so the total field E is equal to 2j E naught sin psi by 2. So the total field 2j E naught sin beta d cos theta by 2. Now the assessment is, for long distance communication, which of the properties mainly necessity for the antenna? It is high directivity, because if high directivity makes the radiation sharper for transmitting and also the receiving. And the second question, which of the following is false about the single antenna for long distance communication? So there are 4 answers. Enlarging may create side lobes, no side lobes, high directivity is required, high gain is required. The answer is, it must be no side lobes. Thank you.